In the previous lecture, we saw how new elements can be inserted into a heap and how existing element can be deleted from it. Now, heap sort algorithm basically use the insertion and deletion steps in the heap. So, say we are given an array A with n elements. The process of sorting the elements of array A using the heap sort is that it has two steps, step 1 and step 2, phase 1 and phase 2. So in the phase 1, you build a heap H out of all the elements of A. So using all the elements of A, you build a heap. Okay, so elements of array A are considered one by one. First element is considered first, then the second element, then third element, and so on. So using all the elements of array A, you build a heap, right? Then in the second phase, you repeatedly delete the root element of the heap H, right? So once you have built the heap completely out of the elements of array A, you start deleting the root element. There are n element in the heap, so you will delete the root n times. And the order of the sorting, whether it is ascending and or descending, depends on the type of the heap. If the heap you build is the max heap, you will get the descending order, right? Because uh, for the first time when you delete the root node, it will be the largest element in the max heap. Okay, so if you are deleting from the max heap, you will get the descending order, and if you are using min heap, you will get the ascending order of the elements of array A. So heap sort algorithm is simple and it uses the insertion and the deletion algorithm in the heap that we discussed in the previous lecture. Okay, so this is the insertion algorithm which insert a new element item into the heap tree containing n elements. Okay, so n elements are already present in the tree and item will be the n plus 1th element. So ins heap insert a new element item into a heap of n elements, and del heap is the algorithm which deletes an element item from a heap containing n elements, right? So these two algorithms will be used in the heap sort. Okay. So two phases. So we have mainly two steps in the heap sort. First, you build a heap using all the elements of array A. Okay, so repeat for j is equal to 1 to n minus 1, insert aj, insert heap, ins heap, aj plus 1. Okay, so A is your heap and j is the current size of heap A, and then you insert the new element of array A, aj plus 1, right? And once you have built the heap in the step 1, you delete the root element repeatedly until the heap becomes empty. Okay, so sort A by repeatedly deleting the root of the h, repeat while n is greater than 1, keep deleting until the heap becomes empty, until it has at least one element. Okay, call del heap. Okay, step 2a, and then set an plus 1 is equal to item. Okay. That is, you store the detail element at location an plus 1. Now the complexity of the heap sort. Okay, so heap is an almost complete binary tree. So its height is log n base 2 if there are n number of nodes in the heap. Okay, so there are two steps in the heap. First you build the heap and then you delete the root repeatedly n times. So complexity of the first step, building heap. Okay, and what is the process of building heap? You insert the elements into the heap, and inserting a single element into the heap of n elements require maximum log n base 2 comparisons. Okay, because when you insert a new element, you add that element in the last, and then you rise that element up to the root. Okay, so it may traverse up along any branch of the heap, and the maximum number of nodes in any branch of the heap is log n base 2, is bounded by log n base 2, because the height of the heap is log n, right? So the complexity, the number of comparison for inserting a single element is bounded by log n. Okay, and since you have to insert n elements, so it will be bounded by n into log n base 2, right? So the complexity of the first step, building heap, is order of n log n. Now phase 2, deleting the root repeatedly. Okay, when you delete the root once, okay, so what we do, you delete the root and then you take the last element of the heap and put at the root position, and then you sync out that root up to its proper position. So again, a single branch of the heap will be traversed down, right? So the number of comparison is again bounded by the maximum number of nodes present in any branch, and that is equal to the height of the heap, log n base 2. So deleting the root once is bounded by log n base 2. Okay, and since you have to delete the root n times, so it will be bounded by log n base 2. Phase 2 complexity is bounded by n log n base 2, right? So these steps, that is the first phase and the second phase in the heap sort, are executed sequentially. Okay, so the overall complexity will be order of n log n. Okay, so order of n log n. This is the complexity of heap sort, right? And you can see that this is the complexity in all the cases. Okay, that is in the average case, in the worst case, okay, and in the best case also. The reason is because a heap is always an almost complete binary tree. A heap cannot be a left or right skewed binary tree, right? So average worst and best case complexity for the heap sort is same, that is order of n log n. Now balanced binary tree, which are also called AVL tree, AVL tree. Okay, so binary search tree store linearly ordered data. Okay, linearly ordered data means because the in-order traversal of the binary search tree gives you the linearly ordered data. Okay, if you traverse the binary search tree in order, you get the data in either ascending or descending order, right? In fact, you get the data in ascending order. Okay, okay. So binary search tree basically store linearly ordered data. You can get the linear order by traversing the in order, uh, by traversing the binary search tree in order, right? So you know that binary search tree can be left or right skewed. Okay, so it means that the height of the binary search tree can be between log n base 2 and n. Okay, if the binary search tree is a complete binary search tree, its height is the minimum log n base 2, and if it is either left skewed or right skewed, its height is maximum, equal to number of elements in the binary search tree. And okay, so these are the minimum and the maximum value for the height of a binary search tree, right? And you know that the number of comparisons depends on the number of elements in a branch, the maximum number of elements in any branch of the binary search tree, right? So since maximum number of elements can be equal to n, so it means that the search complexity in the worst case is order of n. So if the binary search tree is either left skewed or the right skewed, okay, then the maximum number of comparison uh, is the number of elements. That is, the worst case complexity of searching in binary search tree is equal to order of n. Okay. So for example, if the tree is left skewed, you start comparing with the root node. Okay, then in this particular case, then you will compare with this node, then with this, then with this, and then with the leaf node. Okay, so all the elements in this tree will be compared with the new value, right? If the element the if the new element is the smallest one. Okay, so in this particular case, if the binary tree is left skewed or the right skewed, you are getting the worst case complexity. Okay, the reason is that the binary search tree is not balanced, more particularly height balanced. Okay. So if the binary tree is balanced, then the height of the bal- uh, balanced binary tree is around log n base 2. Okay, and if the height is around log n base 2, it means the maximum number of comparison is also around log n base 2 or bounded by log n base 2, or the search complexity in that balanced binary tree is of the order of log n base 2. Okay, even the worst case complexity is also of the order log n base 2. Okay, so in the normal binary tree, the worst case complexity is order of n, but if the binary tree is balanced, its height is always around log n base 2. So the search complexity is also bounded by log n base 2. Okay, so even the worst case complexity is also order of log n base 2. Okay, so to get the worst case complexity equal to log n base 2, you must keep the binary tree balanced all the time. Okay, so first see what is a balanced binary tree. Okay, a balance of a binary tree or a binary search tree can be defined in several ways. Here in this course, we will discuss only the height balanced binary search tree. That is where the balance is defined using the height of the tree. Okay, so height balanced binary search tree are also called AVL search tree. Okay, uh, in fact, if your binary tree is just a binary tree, it is not binary search tree. In that case, the balanced binary tree is called AVL tree. And if your binary tree is also a binary search tree and is a balanced tree, then you will call that tree as AVL search tree, right? So if binary tree is balanced, it is called balanced binary tree or AVL tree. And if your balanced binary tree is also a search tree, then it will be called balanced binary search tree or AVL search tree. Okay, so what is AVL for? AVL is named after Adelson, Lulsky, and Landis. Okay, so these are the persons who proposed the balanced binary tree. So the name of this tree is named after them. Adelson, Lulsky, and Landis, AVL tree. Okay, so this is the definition of balanced binary tree. An empty tree is height balanced. Okay, remember that binary tree can be empty. Okay, so if the tree is empty, it is assumed that it is height balanced. So an empty tree is always height balanced. A non-empty binary tree T is balanced if the left subtree of the root of the tree T is balanced, the right subtree of root of T is also balanced, and third point, the difference between the heights of the left subtree and the right subtree of the root is not more than 1. Right? So the left subtree is balanced, right subtree is balanced, and the difference between the height of left and right subtree of the root of the tree t is not more than 1. Okay, so this definition is recursive. Okay, and you know that each left and right subtree are themselves are themselves binary trees. Okay, so in those subtrees must also satisfy these three conditions. Okay, so in effect you can say that if the condition 3 is true for all the nodes of the binary tree, then that binary tree is a balanced binary tree. Okay, so if for any node the height of if for any node the difference between the height of its left and right subtree is not more than 1, then that tree is a balanced binary tree. Okay, so an empty tree is assumed to have height equal to -1. Okay, -1 because the difference is between the left subtree or the right subtree. Okay, if the height of the right subtree is more than the left subtree, then you will get the balance in negative. Okay, so if the tree is empty, the height is assumed to be -1. Okay, fine. If the tree has a single node, the root node, then its height is equal to 0, right? So balanced binary search tree is known as AVL search tree. Balanced binary tree is known as AVL tree, and balanced binary search trees are known as AVL search trees. Okay. So difference between the height of left and left tree for a node is called its balance factor, and balance factor for a node in balanced binary tree or balanced binary search tree can be either -1, 0, or 1. Okay, but not more than 1. Okay. So if the balance factor for any node is either 2 or 3 or more than 1, okay, then it means that that tree is not balanced. That tree is not height balanced. Okay, for example, now consider this node, this tree. Okay, so the root 3, what is the balance of this? The left subtree height is, in the left subtree there is a single node. Okay, so what is the height of this left subtree? There is single node, the root node of the left subtree, so its height is equal to 0. Okay, so its height is equal to 0. And what is the height of the right subtree of 3? The height of the right subtree of 3 is -1, because the right subtree is empty, and the height of the empty tree or subtree is equal to -1. Okay, so the balance factor for node 3 is equal to the difference between the heights of its left and right subtrees. The height of left subtree is 0, and the height of right subtree -1. 0 minus -1 is turned out to be +1. Okay, so the balance factor for 3 is 1. What is the balance factor for 2? Both left and right subtrees are empty. Okay, so -1 minus -1 gets 0. Okay, so there are only two nodes, and for both of these two nodes, the balance factor is less than 1. Okay, the balance factor is less than 2, right? The mod of the balance factor. So the balance factor can be the 0, 1, or -1. So for 3 it is 1, and for 2 it is 0. It means that this tree is balanced. This is the balanced binary tree, and this is also a balanced search tree because 2 is less than 3 and it is in the left subtree of 3. So it is also a binary search tree. So it is balanced binary search tree. Okay. Now see, if you insert 1 in this balanced binary search tree, you will get this tree. Now check if this tree is balanced binary tree or not. Okay, what is the balance factor for node 3? Okay, this is the left subtree. What is the height of its left subtree? 2 minus height of right subtree empty. Okay, sorry. The height of the left subtree is 1. Okay, because this is the left subtree and the height of the left subtree is 1. Okay, minus what is the height of right subtree? Right subtree is empty, so minus 1, 2. The balance factor for 3 is 2. What is the balance factor for 2? It's 1, right? And what is the balance factor of 1? It's equal to 0. Now, since the balance factor for node 3 is 2, so this binary search tree is not balanced because you have a node, the root node, which does not have a balance factor equal to either 0 or minus 1 or 1. For 3, balance factor is, for node 3, the balance factor is 2. So this tree is not a balanced binary search tree. Okay, so what can you do? Okay, can you do something to make this binary search tree balanced? Okay, so what is the important property of the binary search tree? The in-order traversal of the BST gives you the ascending order of elements. Okay, so what you can do, you can modify the structure of binary search tree so that this property is fulfilled. Okay, can you modify this tree in such a way that if you traverse that modified tree in order, you get the ascending order, the same ascending order 1, 2, 3. Okay, so what you can do, there are in fact ways using which you can modify the binary search tree and you get the same in order traverse. Okay, so for example, in this particular example, what you will do, you will promote the node 2 to the root. Okay, this was the old node 2 and this is move up to the root. The node 2 is made the root of this tree and the node 3 is demoted to be new nodes, new root nodes, node 2, right? And the 1 remains the left child of 2. So this is the new structure. Okay, after modification, and you can see that the in order traversal is same. Okay, first left, then the root, and then the right, 1, 2, 3. Okay, so this property is still fulfilled. Okay, and this is a binary search tree and this is also balanced. Okay, so the BF for node 2 is 0 and for node 1 it is also 0 and for node 3 it is also 0. So this is a binary search tree and in the in order traversal it still gives you the same thing, the same order 1, 2, 3. Okay, right. Now consider another example. Now in this tree is balanced. Okay, this the BF factor is 1 and the balance factor for node 1 is 0. Now insert 2. So here 2 will be inserted. 2 is less than 3, so you go to the left subtree. Okay, and 2 is larger than 1, so you will create a new node for 2 in the right subtree of node 1 like this. Okay, now the balance factor for node 3 becomes 2. So this tree is not balanced. This is a binary search tree, but it is not balanced. Okay, so what will you do? You can modify this binary tree to make it balanced by and keeping the in order property intact. So what you will do in this case, you will promote 2 to the root node and assign 1 and 3 to be its children. Okay, so finally after doing this you get this. This tree is balanced balance factor for all the three nodes are 0, and if you traverse this node in order, you get the same result, same ascending order of the elements 1, 2, 3. Okay. So so basically we are performing some modifications, and these modifications are called rotations. Okay, and these rotations are, you know, in particular situations, you perform a kind of rotation to make an unbalanced binary search tree a balanced binary search tree, right? So we will see. In fact, there are four kind of rotations which can be performed in four different situations to make the binary search tree balanced. Okay. These are some examples of balanced trees, balanced binary trees or AVL trees. Okay, you can see that height of that is, you can see that the balance factor for each node is either 0 or -1 or 1 in these examples of the AVL tree. Another example, okay, and this AVL tree is somewhat larger, containing 42 nodes. Okay, and you can again check that the balance factor of any node is not more than 1. Okay, so this is also a balanced binary tree of height 4. Okay, if the tree is a complete tree, okay, then you have an upper bound on the number of nodes in the AVL tree. Okay, and that upper bound is 2 to the power s plus 1 minus 1. That's the number of if the height is h in the complete binary tree, then number of nodes is 2 to the power h plus 1 minus 1. Okay, we have already discussed this. Okay, now rotations. How the rotations are performed. Okay, rotations are performed to maintain AVL tree balance. Okay, that is when a balanced binary tree can become unbalanced when you insert an element, okay, and the balance factor of any node becomes other than 0, -1 or 1. Okay, likewise, if you remove a node from a balanced binary tree, in that case also the balance factor of any node can become other than -1, 0 or 1. Okay, so if insertion or deletion makes a binary tree unbalanced, you can perform rotations to make it to make the tree balanced. Okay, so how the rotations are performed? Rotations are performed around a node. Okay, and which node? And that node is uh, you identify node A, for which balance factor is neither -1, 0 or 1. Okay, and that node is nearest ancestor to the inserted node on the path from the inserted node up to the root node. Okay, so say you have inserted a new node, node X. Okay, and say this is your root node. So you have inserted this new node, node X, and this is the path from the inserted node X up to the root node. Okay, so you find a node A on this path which is nearest to the node X, and the balance factor for node A is not either 0, -1 or 1. Okay, so first you find this node. Okay, so what are the conditions for this node? This node is on the path from the inserted node X to the root node, and the balance factor of that node is neither -1, 0 or 1, and that node is the nearest ancestor. Okay, nearest ancestor means because there might be several nodes on path from X to root node for which the balance is neither -1, 0 or 1. Okay, for example, there might be another node on this path, node B, for which balance factor is not equal to 0, -1 or 1. Okay. So you have to select this node which is nearest to the inserted node X. Okay. So once you have selected this node A, then you can perform one of these four rotations depending on the situation. Okay. So rotation can be LL, RR, LR or RL. LL is for left left, RR is for right right, LR is for left right, and RL is for right left. Okay. So left left rotation first. LL rotation is performed when the inserted node X is in the left subtree of the left subtree of the node A. Okay. So first you find the node A. Okay. And then if the inserted node is in the left subtree of the left subtree of node A, you will perform left rotation. And if the inserted node X is in the right subtree of the right subtree of node A, you perform RR rotation. And if the inserted node X is in the right subtree of the left subtree of node A, you perform LR notation, left right notation. And if the inserted node X is in the left subtree of the right subtree of node A, you perform RL, or right left rotation. Okay. Now we will see these rotation one by one. First LL. Okay. So see this tree. This tree is an AVL tree, balanced binary tree. Okay. So here two nodes are depicted, node A and node B. Okay. And these rectangles are subtrees and subtrees of height h. Okay. So these subtrees might have several number of elements. The height of these subtrees are equal to h. Okay. So here root node is A. Okay. Its left subtree, sorry, its right subtree is AR, and height is equal to h. Okay. And the left subtree of node A is this one. Okay. The root of the left subtree of root A is node B. Okay, BL is the left subtree of node B and BR is the right subtree of node B. Okay, and height of the BL is equal to h, right? Okay, so and also the height of the right subtree BR is also equal to h. Okay, so if you find the balance factor for these two nodes, node B and node A, you will get as +1 and 0 for node A and node B respectively. Okay. So this is a balance binary search tree, AVL search tree, right? Now insert a new element X into BL. Okay, what is BL? BL is in the left subtree of the left subtree of node A. Okay. Node A is this, its left subtree is this, okay, and the left subtree of the left subtree of node A is this, BL, right? So insert new element X into BL. Okay, so you can see that X is inserted over here. When you insert X, that is, you are inserting a new element X, the height of the BL will increase by 1, might increase by 1. Okay, in this particular case, we assume that the insertion of new element X increases the height of BL by 1. So now it becomes H plus 1. Okay, so the height of BR is h, and the height of BL after inserting x is now h plus 1. Okay, so what is the balance factor of node B? It becomes plus 1. And what is the balance factor of node A now? It is plus 2 now. Okay, so now this tree is not balanced. Okay, so to make it balanced, you will perform rotation. Okay, so first you find the node around which you have to perform the rotation. Okay, so here the node X. So first find the path from this node X up to the root. So this is the path. Okay, now the node for which the balance factor is not equal to -1, 0, 1. Okay, so node B has balance factor equal to +1, and node A has balance factor equal to +2, right? And you can see that all the nodes in BL also has balance factor equal to either 0, -1 or 1. Okay, so node A is the node which is on the path from node X to the root node, have balance equal to +2, not equal to -1, 0, 1, and this is the nearest node, that this is the nearest such node to the inserted node X. So we have to perform the insertion around this node X. How the insertion will be performed? Sorry, how the rotation will be performed? And since node X is in the left subtree of the left subtree of node A, okay, this is node A, left subtree is this, and node X is also in the left subtree of the left subtree of node A, right? So since node X is in the left subtree of the left subtree of node A around which you are going to perform rotation, so you will perform left rotation, LL rotation. Okay. So how the left rotation is performed? It is rotated so as to allow B to be the root, that is the left child of node A will become the root. B is the left child of node A. Okay, what is node A? Around which node we are performing rotation. So the left child of node A, that is node B, will become the new root. Okay, and the BL, that is the left child of node B, will remain the left child of node B. Okay, and node A will become the right child of node B. Okay, the right child of node A, AR, that is the right subtree, will remain same, that is it will remain the right subtree of node A, but the right subtree of node B will become the left subtree of node A. Okay, that is the node B. What is node B? Node B is the left child of node A. So left child of node A will become the root. Its left child will remain the same, BL. Okay. Node A will become the right child of new node B, new root node B. Okay. Its right child will remain the same, AR. Okay. And the left child, sorry, the right subtree of node B will become now the left subtree of node A. Okay. So after performing these, you will get this binary search tree, and you can see that this binary search tree is balanced binary search tree. Okay, so now see an example. Say this is an AVL search tree. Okay, the BF for all the nodes are written with them. Okay, so 0 or 1, so this is a balanced binary search tree. Now insert 36. Okay, so 36 is less than 96. It is also less than 85 and also less than 64. Okay, so 36 is inserted in the binary search tree. This is the obtained binary search tree after inserting 36. Now find the BF for all the nodes. So balance factor for all the nodes are 0, 1, 0 or 1 except the root node 96. It is +2 now. So this is not a balanced tree. So how will you perform the rotation, and which rotation? Okay, this is the root node and this is the new node 36. Okay, and this is the path from the new node to the root node. Now along this path, find node A around which you have to perform the rotation. Okay, there is only one node which does not have BF equal to 0, -101, and that is the root node itself. Okay, 96. So this is your node A. Fine. And now perform rotation. And which rotation you will perform? Okay, since new node L is in the left subtree of the left subtree of node A, this is the left subtree of node A, and 36 is in the left subtree of the left subtree of node A. So you will perform LL notation. How to perform LL notation? Okay, you have found node A. The left child of node A will become the root. So 85, the left child of node A. So 85 will become the root. Okay. The so here 85 is basically the node B. Okay. So node B will become the root. Fine. Its left subtree, that is BL, will remain same. So this is BL. It will remain same. Okay. It will remain the left subtree of the node B. Okay. Node A will become the right child of node B. Okay, so 96 will become the right child of node B. Its right child, the old right child will remain same, that is 110 will remain as the old position. Okay, right child of 96, and the right subtree of node B will become the left subtree of node A. Fine. So this is the obtained search tree after performing LL rotation around node A 96. And you can see now this is a balanced binary search tree because the balance factor for each node is either 0 or +1. Okay. Now RR rotation is performed when the inserted node is in the right subtree of the right subtree. Okay. So again, same kind of rotations, same kind of operations are performed. That is, first you find node A, okay, and then say the right child of node A is node B. Okay, to perform the RR rotation, what you do? Okay, it is just reverse of the LL rotation. That is, now the right child node B will become the root. Okay, node A will become the left child of node B. Okay, its left child will remain intact. That is, node A's left subtree will remain intact, and the left subtree of node B will now become the right subtree of node A. Okay, so its RR notation is basically just opposite of the Allen notation. You just replace left with right and right with left. You will get the RR rotation from left LL rotation. Okay. An example of RR rotation. Okay, this is a balanced binary tree because BF for each node is either -1 or 0. Now insert 65. 65 will be inserted over here. Okay, the node A's balance factor will become -2. So it is, this tree is not balanced now. So you will perform RR rotation because 65 is in the right subtree of the right subtree of node A. Okay, so RR rotation will be performed around node A. How? Node A is 34 and node B is 44. Okay, so now node B, that is the right child of node A, will become the root. So 44 becomes the root. Okay, node A will become the left child of node B. Okay, its right child, that is node A's right child, will remain same. Sorry, left child will remain same, and uh, the right child of node B will also remain same. Okay, but the left subtree of the node B will become the right subtree of node A. Okay, let's compute the RR rotation. And you can see that the BF for each node is either 0 or -1. Okay, so this is the AVL search tree. So remaining notation, that is LR and RL, will be discussed in the next lecture.